bento ng sasabihin. Ano? So pagka hindi ako nakapag-prepare ng mahabang lecture, kaya ko pa rin ubusin yung 1.5 hours para sa kakukwento. Alright, kahit 2-page lang yung presentation o 2-page lang yung lecture notes. Anyway, let's start. Good morning again, everyone. So ngayon ipapagpatuloy natin yung journey natin on lecture notes number 3, which is about limits of functions. Actually, not just limits, but this is about limits and continuity. All right. So last time, anong ginawa natin? Na-tie up na natin yung konsepto ng or define natin ano yung pagiging continuous. And we have seen that continuity here in Math 155 is a bit more general than the concept of continuity that we discussed in Math 36. Specifically, dun sa konsepto ng ang mga continuous functions ay yung mga functions at yung mga functions lamang na kaya nating i-drawing over an interval without lifting our pen. Right? So if we need to lift our pen for whatever reasons or for some reasons para ma-drawing yung graph ng isang function, then we said back then in 36 na discontinuous na yung function na yan. But the way we define continuity here in Math 155, merong mga functions na kailangan talaga nating i-lift yung pen natin para ma-drawing yung graph niya, but still that function can be considered to be continuous. And an example for that is any function that is defined over a set with isolated points. Because we said that isolated points are yung isang function ay laging continuous. Kahit ano pang function yan, lagi siyang continuous kahit na anong isolated point ng domain. Right? And I think that makes sense because if you have an isolated point, ibig sabihin wala siyang katabing mga elements ng domain. So kung ito yung isolated point natin na si x sub 0, right? Wala siyang mga kapitbahay. There is a window na wala siyang kapitbahay na iba pang elements ng domain. Halimbawa, ito na yung pinakamalapit na kapitbahay niya na element ng domain, si x1 at saka si x2. So since there are no domain elements in the open interval x1 to x2, then ibig sabihin, kailangan talaga nating i-drawing yung graph sa kanan ni x1, tapos i-lift yung pen natin para ma-drawing yung function value kay x2, tapos tatalo na naman yan dun sa papunta kay x2 and so on, right? So in this case, if you look at the graph and you have this Math 36 notion, then sabi mo, discontinuous yung function kasi may putol yung graph. But in Math 155, we also consider the domain kasi unfair nga naman na i-require na ma-drawing natin yung graph ng function without lifting our pen, kahit na wala namang domain elements dito sa immediate kaliwa at immediate kanan ni x sub 0. If there is, or if there are no domain elements there, then there's no point in requiring drawing the graph over that interval without lifting our pen. Right? So ngayon, yung konsepto ng continuity hindi lang nakatali dun sa function values and their behavior kasi nga ngayon tinitingnan din natin yung itsura ng domain. All right? And I think that's a fairer a fairer characterization for continuity than what we had in Math 36. Okay? So, and then we develop some sequential criterion for continuity. So I guess kompleto na yung extension natin ng continuity from sequences papunta sa real valued functions or sa functions na ang domain ay subsets ni R. So for today, we'll talk about continuity on a compact set. Now, ang pagiging continuous kasi ay isa sa mga pinakamagandang properties that a function can have. Remember, there are some results probably that you encountered in your previous math courses when you say na, mag-hold lang itong theorem na to for nice functions. This result will only be true for good behaving functions, all right? And usually that good behavior or that being nice is usually attached to continuity of functions. Kasi napakaganda ng property ng continuous functions. And most of calculus depends on an assumption of continuity. Yun nga lang kasi nung mga unang panahon, yung kilala lang ng mga tao o ang ina-accept nila to be functions ay mga continuous na. But in the advent of axiomatization of branches of mathematics, specifically real analysis, na natutunan ng mga tao na, alright, meron nga palang mga discontinuous functions. Some of them arise in practical applications, right? Kaya lang, hindi swaswak or hindi sila papasok dun sa traditional notion ng calculus o dun sa mga traditional results in calculus, all right? So, but anyway, that interest in continuous functions is further fueled by the fact that hindi lang pala, kahit hindi lang pala mga continuous functions ang mga nicely behaving, ano? So, lahat pala, merong isang result, and this is part of what we call Littlewood's principles sa analysis, na sabi niya, parang lahat ng mga nicely behaving functions ay almost continuous, or almost, or in other words, kapag meron kang isang function na maganda yung behavior, then siya ay continuous almost everywhere. And yung term almost everywhere, it's a technical term in mathematics. I-define ko sa inyo later when we go to integration, kailan nasasabi yung almost everywhere. But essentially that is, so a nice function is almost, or is, di pala almost. Any nice function is at least almost a continuous function. All right? So yun yung mga nice functions. Bakit? Kasi maraming properties ang napreserve ng continuity. All right? Because remember, a function, you can think of a function as a process. Maglalagay ka ng input x, makukuha mo yung output f of x. And it is nice to see anong mga property ng input x yung napreserve doon sa output f of x. All right? Especially for nicely behaving maps. And we said na yung mga nicely behaving maps usually ay mga continuous functions. All right? So we will investigate a little bit today ano yung mga properties ng continuity, ano yung mga properties ang napreserve ng continuity. All right? And what are their implications? Actually, isa lang yung itetest. Actually, tatlo yung itetest natin, pero yung isa, makakuha tayo ng significant insights. All right? Now, just to recall, kung napanood nyo hopefully yung recording na pinapanood ko sa inyo about the proof ng composition ng continuity ng composition ng functions, you will see there that we define the image of a set A or a subset A of the domain of f under the function f, right? So kung meron ko isang function f na ang domain ay set E papunta sa set of real numbers, and a set A is a subset of the domain, then f bracket A is our notation for the collection of all possible values of f of x for all x coming from the set A. So pag kinolekta mo yung function values ng mga miyembro ni capital A, ang tawag natin sa set na yon ay f bracket A, right? Or in other words, that's the image of A under f. And then some properties for this set, we say that f is bounded if and only if f bracket E is bounded. Ibig sabihin, yung set of all function values ay may upper bound at saka may lower bound. Kasi yun yung f bracket E. Kasi si E yung entire domain, so f bracket E represents, actually this represents the range of the function, the set of all possible function values. All right? So ito yung characterization natin for boundedness of a function f. All right? So gusto mo, kung kinolekta mo, okay na pala yun. Ayoko nang pahabain yun. And then, all right, and corollary to that, we say that f is bounded on a specific set A if and only if f bracket A is bounded. All right? So yan yung pagiging bounded ng isang function. Nakatali siya dun sa pagiging bounded ng image ng isang set under that function. Okay? Now, as I've mentioned, we will look at interesting properties that are preserved by continuous functions. Actually, we'll talk about, I think, 3 today. Tingnan natin kung na-preserve ba ng isang continuous function ang pagiging open ng isang set, pagiging closed ng isang set, at pagiging compact ng isang set. All right? So, imagine it this way. Suppose the function f is defined with domain E. Tapos kukuha ako ng isang open subset ni E. Kukunin ko halimbawa si A ay open subset ni E. All right. My question is f bracket A also an open subset of, it's also an open set, all right? So kung si A ay open subset ni E, all right? Or siguro more properly, it is a subset of E that is open, okay? So kung meron kang isang open set, pagka ba yung mga elements ng open set na yon ipinasok ko dun sa function f, yung makukuha ko bang image nung open set na yon ay open pa rin. Remember, sa pagiging open, dapat lahat ng points na interior. Ibig sabihin, dapat merong epsilon neighborhood around all members of that set that is properly contained in the set itself. All right? Another question that we will post is, if I have a closed set, all right, that is a subset of the domain, then is the image of that closed set also closed? And accordingly, ganun din yung tanong natin about compactness. All right? So the first two questions are more easily solved and they are solved in the negative. Pag gusto mong ipakita na hindi totoo ang isang bagay sa math, kailangan mo lang ng isang counter example. All right? Lalo na kung yung definition mo, hindi pala lalo na. Kung yung definition mo dapat ay for all. Okay? Now, if we take, meron dito mga counter examples na binigay. Okay. Kinuha si x squared. Yes, David, you have a question?
Yes po, sir. Tungkol po dun sa umpisa po nung definition ba yan? Why do you say po na image of A? Ano po yung, nahirapan po akong i-conceptualize yung difference between an image of A and yung range po.
Okay. Nice question, David. Yeah. Kapag ka sinabing nating range, siya yung image ng buong domain. Okay. Tinatawag natin siyang image kasi parang ito yung resulta after you put in you perform the function f on a domain element. So pwede mong isipin yung function f ay parang maskara, all right? Meron kang isang tao, tapos pag in-evaluate mo yung function value niya, parang magkakaroon lang siya ng mask, tapos yung image, yun yung result ng pagsusuot ng mask. So parang ganun din. So ang result ng function evaluation na yung image ng isang domain element, all right? Tapos kapag pagka kinuha mo yung image ng lahat ng mga domain elements, yun yung makukuha nating range. So when we say image of the function f, siya yung range o siya yung collection ng lahat ng mga function values ng domain elements. Alright? Pero yung f bracket A ay image ng isang mas maliit na set ng domain element. So halimbawa, ito yung domain E natin. Si set A ay ito lamang. Alright? So subset siya ni E. Tapos yung range, siya yung set ng lahat ng function values. So ibig sabihin, kung ito si kung ito si E, yung malaking circle, pinerform ko si F, makukuha kong mga function values ay ito. Ito yung range of F or the image of F, or pwede natin tingnan siya yung F bracket E, collection of all images. Pero pag tinignan natin yung F bracket A, siya lamang ay ito. Siya lamang yung mga function values ng mga elements na nanggagaling dun sa subset A ng domain. So yung F bracket A, mas maliit siya sa range. Subset lang siya ng range. Kasi yung range, siya yung lahat ng posibleng function values. Pero yung F bracket A, siya lang yung lahat ng mga posibleng function values ng mga elements ni capital A. Alright, so mas maliit siya sa range. Does that make sense, David?
Thank you, sir.
Alright, so mas maliit yan. Alright. Okay, now going back to the question. Kapag kasi A ba na to ay, Kapag kasi A ba na ito ay open, yung image niya ba under f ay open pa rin? So ibig sabihin, na-preserve ba ng continuous function yung pagiging open ng isang set? If my input are elements of an open set, will their image result to an open set as well? The answer is no, hindi necessary. Alright? Posibleng meron kang isang open set na pinasok mo sa isang continuous function, pero yung function values will not constitute an open set. And an easy example is the quadratic function f of x equals x squared. Okay, So, ang idea rito ay, okay, kung gusto ko yung gamitin, kailangan ko mag-isip ng isang open subset ng domain ni x squared ng image under f ay hindi na open. Alright? And the textbook gives us one quick example. Consider natin si set A to be the open interval -1 to 1. We already learned, and if you're doing a homework or a problem set, you don't need to prove anymore that that any open interval is an open set. So pwede nyo sabihin, sir, yung set A na yan, dahil siya ay open interval, siya ay isang open set. Tapos, paano mo makukuha yung F bracket A? Yung F bracket A, maybe it is a better explanation of David's question kanina. Kukunin mo lang lahat ng function values ng mga elements from -1 to 1. Okay? And it is easy to see na, okay, siguro tingnan natin yung graph, right? So, kung graphical tayo mag-isip, ito yung y equals x squared. So, ang range niya ay from 0 to positive infinity. Yun yung image ni f. Pero pag titingnan natin yung image ni a under f, si a ay yung interval -1 to 1 lamang. So, ibig sabihin, ito lang yon. Okay? Ito lang yung f bracket a. Kung ito si set a. Kokolektahin mo lang lahat ng function values ng mga members ni capital A. Since capital A consists of real numbers that are greater than -1 but less than +1, yung f bracket A will be starting from 0 papunta na kay 1, and 1 is not included. Alright? Kasi si 1, ay nagiging function value lang kapag si x ay eksaktong 1 or -1. Pero dahil si -1 at saka si 1 ay hindi kasama kay capital A, then we are forced to conclude that f bracket A is the half-closed, half-open interval 0 to 1. Okay? Kinolekta mo lang yung images ng mga elements ni capital A. And obviously, this guy is neither open nor closed. So, ibig sabihin, nakakita tayo ng isang example, isang open set, the open interval -1 to 1, na ang result after we perform the function f, or the operation f onto A, ang nangyayari, nakakakuha tayo ng isang set na hindi na open. So, yung pagiging open, hindi na preserve ng continuous functions. But if you have taken topology, makikita nyo na yung inverse image, yung nakakapag-preserve ng openness. Alright? Ano nga ba yung, tama nga ba, ang theorem nyo sa topology ay ang isang function ay continuous if and only if the inverse image of an open set is also open. Alright? Tama nga ba? Sana tama yung topology ko. Pala yung problema, no? Dapat sigurado ako pag nag-adlib kasi naka-record nga pala tayo. But I think that's right. So you can fact check me on that and let me know if something is missing from my from that statement kung nag-topology na kayo. But anyway, if you haven't taken topology, then never mind. All right. So next question. Napreserve ba yung pagiging closed? The answer is no. Hindi laging napreserve yung pagiging closed. Merong mga closed sets na ang image nila under a continuous function is not closed. Okay? Merong mga closed set na napreserve. Halimbawa, si x squared. Si x squared, pag kinuha mo yung isang isang closed interval, I think the image will still be a closed interval. Tama ba? So, meron kang closed interval AB, ang function value under x squared will also belong to a closed interval. So, okay, there are some instances wherein pagiging closed is preserved, pero hindi palagi. And the handout gives us a nice example. Consider daw natin itong closed set, 0 to positive infinity, the set of all non-negative real numbers. Pero pagka ipinasok ko yan sa function of 1 over 1 plus x squared, and this is a rational function, the numerator is always continuous. It's the constant function. The denominator 1 plus x squared is also continuous. This is always defined for any x. So by the algebraic continuity theorems that we met last time, the quotient of two continuous functions is also continuous. So continuous si G. Okay? Tapos, pero kapag kinonsider ko yung set of all non-negative real numbers which is closed, pag kinuha ko yung image nun, hindi na closed yung makukuha kong image. Kasi pag nag-plug in ako dito ng mga non-negative numbers, 0 to positive infinity, alright? Tingnan nga natin ano yung mangyari. Pag nag-plug in tayo ng 0, makukuha ko si 1. Pag nag-plug in ako ng something that is greater than 0, the denominator will be greater than 1. So this will be less than 1. The quotient will be less than 1. All right. So basically, you can check that the image of this set A is equal to the half open, half closed interval 0 to 1, which is neither open nor closed. So ibig sabihin, nakakita tayo ng example ng isang closed set na hindi naman siya, na ang image niya ay hindi na natiling closed under a continuous map. Right? So lesson here, hindi na preserve ang pagiging closed. But ibang usapan kapag compact yung set natin. Alright? So remember, we characterize compact sets to be those sets that are both closed and bounded. So kapag meron ka palang, kung meron kang isang function, kung meron kang isang set na closed, alright? Kung closed lang yung pagiging property niya, hindi necessarily magpa-follow na yung image niya under a continuous function is also closed. Alright? Pero pag dinagdagan mo ng boundedness, yung subset ng domain, so naging closed and bounded na siya. Remember, a set is closed and bounded if and only if it is compact. All right? So ang image niya na ay nananatiling compact. All right? So that's what Theorem 3.6 is telling us. If you have a function f defined on a set E to the set R that is continuous, and if you get a compact set K that is a subset of the domain, then f bracket K is also compact. Okay? Sufficient pala na magdagdag na lang tayo ng boundedness para ma-preserve yung pagiging closed at pagiging bounded ng isang set under the continuous function f. Now, sige, tingnan natin yung proof. But in the proof, I'll use the definition of pagiging compact. Kailan nga compact ang isang set? Yung pagiging closed and bounded, theorem lang natin yon. Mas madaling gamitin sa proof yung definition ng mga true subsequences. So ang sabi ng pagiging compact ay compact ang isang set if and only if kahit na anong sequence sa loob ng set K, meron siyang isang convergent subsequence. All right? So yun yung pagiging compact. So let's try to see it. Let's try to prove Theorem 3.6. Ano? So gusto nating i-prove na si f bracket K ay compact. So ibig sabihin, pag nag-consider ako ng kahit na anong sequence sa loob ni f bracket K, gusto kong makakita ng isang subsequence na nagko-converge sa loob ni f bracket K. So yun yung kailangan para mapakita na siya ay pagiging compact, and our only assumptions are f is continuous and K is a compact set. All right? So let me go through the proof. Okay lang ba na daanan ko yung mga proof? Hindi ko i-rewrite yung mga proof kasi I was reading the notes kanina at merong mga little typo errors na hindi ko na-correct last semester. Chinek ko kung bakit hindi ko sila na-correct kasi pala sinulat ko yung proof uli from scratch. Tinakluban ko yung proof, nagsulat ako ng sarili kong proof, right? So kaya hindi ko nakalimutan kong i-edit in the next iteration ng lecture notes na nasa inyo. But let us go through the proofs and insert some corrections if necessary. Tapos before you go to the problem set, probably over the weekend, I'll upload a new version of the lecture notes for Unit 3, reflecting the corrections na mapapansin natin today. Okay? So, daanan natin yung proof. Ano yung sinasabi ng proof? Well, dahil gusto kong ipakita na si f bracket K ay compact, mag-consider ako ng isang arbitrary sequence sa loob ni f bracket K. And again, the goal here is to show that f bracket K is compact, and to do so, we want to show that there exists a subsequence na nagko-converge sa loob ni f bracket K. Alright? Gagamitin natin yung continuity at pagiging compact ni K. So tingnan natin, ano yung sinasabi niya? Well, si C sub n ay, okay, so yung mga C sub n ay element ng f bracket K. By definition of f bracket K, ibig sabihin si z sub n ay function value ng isang element ni k. Right? So remember, f bracket k is the set of all elements of is the set of all function values of elements of k. Ito yung mga images ng mga miyembro ni capital K. So kung si Zn ay element ni f bracket k, dapat si Zn ay function value ng at least isang element ni capital K. And that is what we're saying here. There exists some x sub n inside capital K such that f of xn is equal to Zn. Right? So dahil nangyayari yun, pwede kong makonstruct yung sequence na x sub n, alright? Ng x sub n ay yung pre-image ni c sub n. Kung sino yung element ni k na nagbigay sa akin ng function value na c sub n, siya yung tatawagin kong x sub n. And by doing so, I can create a sequence ng mga xn na nasa loob ni k. Is that okay? Medyo kailangan ko lang i-rewrite ng konti itong proof na to. Alright? So, kailangan ko sabihin paano ko kinonstruct yung x sub n. Kinonstruct ko yung sequence x sub n by selecting x sub n to be one of the pre-images of z sub n that belongs to k. Alright? So, bakit ba gusto ko na yung sequence xn ay maging element ni k? Kasi para magamit ko yung assumption na si k ay compact. Okay? So, dahil itong sequence na to ay nasa loob ng isang compact set, by definition ng pagiging compact, there will exist a subsequence x sub n sub k such that x sub n sub k will converge to some element of the set k. Kasi nga compact siya, so meron siyang subsequence na nagko-converge sa isang element ng set k. Alright? Is everything good so far? Medyo ang tricky dito ay yung pag-recall ng definition ng compactness. Ano? But with that in mind, sana clear pa yung mga nangyayari. Okay, can you react a little bit? Talagang NR, guys. Ano yung tanong nyo? Kung may magulo. Wala pa naman. Okay, hopefully everything is good so far. So nagamit ko na yung pagiging compact. So tingnan ko paano ko magagamit yung pagiging ang pagiging continuous. Yeah, that's understandable, David, na mahirap maalala yung pagiging compact. That's why some books usually define yung pagiging compact as pagiging closed and bounded. Kasi yun yung madaling characterization ng compactness. Pero mas madali kasing gamitin sa proofs yung definition natin ng compactness na ang isang set ay compact if and only if kumuha ka ng if and only if kahit anong sequence sa loob ng set na yon ay laging may convergent subsequence na ang limit ay nasa loob ng set na yon. And that's essentially what we applied in these lines. We applied here. Okay. Now, gagamitin ko ngayon yung pagiging continuous ni function f para mapakita na merong subsequence si Zn na nagko-converge sa loob ni f bracket k. Alright? But remember our characterization of continuity. Dahil si f ay continuous, tapos yung sequence x sub n sub k ay nagko-converge kay x sub 0, then yung sequence na mga function values ni x sub n k ay magko-converge din dun sa function value ni x sub 0. And that is true since f is continuous nga. All right? So that means, yeah, okay, this is continuous. So this is true. The sequence of function values of elements of the subsequence is convergent, and it converges to f of x sub 0. Pero ano nga ba yung itsura ng mga to? Yung mga f of x sub n sub k, sila lamang ay mga c sub n sub k. Alright? Kasi yung mga c sub n, sila ay function values ng mga x sub n. So yung mga c sub n k, sila ay mga function values ng mga x sub n k. So this guy, or the sequence of f of x sub n k, which is equal to c sub n k, ay isang subsequence ng c sub n. At nakita na natin na yung sequence na yon ay convergent. So we're halfway done. The only thing that we need to check is nagko-converge ba yung subsequence na yon, yung C sub nk, sa isang element ni f bracket k? But we know that the sequence will converge to f of x sub 0. But the nice thing is that the compactness of k guarantees that x sub 0 is in capital K. Dahil si x sub 0 ay nakay capital K, so si f of x sub 0 ay nakay f bracket K. So that means our subsequence z sub nk converges to a member of f bracket k. And that is essentially the requirement for compactness. Kung may terma na compactness. Kung wala man, kinukoin ko na ngayon yung compactness. All right? So therefore, we can say that indeed f bracket k is compact. In other words, the continuous image of a compact set is also compact. All right? So any questions with the proof? Medyo masalimuot yung proof. Pero masalimuot lang siya kasi gawa ng definition ng compactness. Ano? Pero I hope once you go to the details, maintindihan nyo kung ano yung mga nangyari. It's just a play on the definition of compactness and the sequential criterion for continuity. All right? Okay, can we move on to Theorem 3.7? Okay, now, may magandang implication yung preservation ng pagiging compact, right? And one nice consequence of the preservation of compact sets is your good old extreme value theorem. So math 36 is waving. Tandaan niyo ba yung EVT sa math 36? Ginamit niyo to nung nag-optimization kayo. Kumuha kayo ng maximum or minimum ng isang function. Well, the math 36 version of the extreme value theorem tells us na isang continuous function ay nagkakaroon ng maximum at saka minimum sa kahit anong open interval. Alright? So kapag ka ang set of consideration mo ay closed interval, tapos meron kang isang continuous function, yung continuous function na yun will attain its maximum and minimum, or will attain a maximum and minimum on that closed interval. Right? So that's the thing. Pero dito mas generic yung titingnan natin kasi hindi lang pala necessarily sa closed interval siya nangyayari, right? So yung EVT ay totoo sa kahit na anong compact set. Yun nga lang nagkataon ng pinakamadaling example ng mga compact sets ay yung mga closed intervals kasi sila ay closed and bounded. But any set that is closed and bounded is compact, so mag-hold pa rin yung extreme value theorem sa kanila. Ano ba yung sinasabi ngayon? Or paano natin i-state ang extreme value theorem ngayon? Well, it is stated this way. We consider a function f whose domain is the set E, and that f is continuous on a compact subset K of E. Then it says that f attains a maximum and minimum value on K. That is, merong x sub little m at saka x sub big M in capital K such that f of x sub m is smaller than all function values of elements of K, and f of x sub capital M is larger than any function value of any member of capital A. All right? So basically, pinalitan lang natin yung closed interval sa math 36 by pagiging compact. All right? Now, it will be easier to prove this if we will accept the following lemma. I was thinking kanina to give you lemma 3.1 as part of your problem set, but pinag-iisipan ko pa. Ano ba yung sinasabi ng lemma 3.1? Kapag ka si K ay compact, then yung supremum ni K at saka yung infimum ni K ay parehas nag-exist at sila ay membro parehas ni capital K. Medyo madaya kasi yung halos bulk ng work to prove the extreme value theorem is actually the lemma itself. All right? So, karamihan nung kailangan gawin para sa proof ng EVT ay ginawa na dun sa proof ng lemma 3.1. Okay. But a sketch of proof of lemma 3.1 para kung gusto niyo siyang i-try later. Kung ayaw niyong mapakinggan yung proof, gusto niyo siyang gawin ng sarili, so mute niyo muna ako. Alright? Kasi spoil ko yung sketch ng proof. Okay, paano natin ipo-prove na kung si K ay compact, then yung supremum at infimum niya ay nasa loob niya. Okay? Now, K is compact, so ibig sabihin si K ay bounded. Kasi compact even only if closed and bounded. So K is compact implies K is bounded. Dahil si K ay bounded, ibig sabihin meron siyang lower bound at saka meron siyang upper bound. By the LUB property and a corollary to the LUB property, dahil meron siyang lower bound at upper bound, meron siyang greatest lower bound at meron siyang least upper bound. So the infimum and the supremum exist. Pero saan siya nag-exist? Nag-exist siya as a real number. So what's left to be shown is that the infimum and supremum are both members of K. Yung kailangan nating i-argue. Yun yung kulang pa dun sa proof. Well, you can argue it this way. Gamitin natin yung pagiging compact niya. Nagamit ko na yung boundedness. So gamitin ko pa yung isang property ng pagiging compact. Kung siya ay compact, ibig sabihin dapat siya ay closed din. Alright? So kung closed yung isang set E, pwede akong mag-define, kung closed si set K, pwede akong mag-define na, okay, siya ay closed. So ibig sabihin, laman niya lahat ng kanyang mga limit points. Alright? So laman niya lahat ng mga limit points niya. So ibig sabihin, pwede akong mag-consider na isang monotonic increasing sequence sa loob ni capital K. Right? So si K ay isang set, magko-consider ako ng kahit na anong monotonically increasing sequence kay K. Tapos yung dahil tama ba? Close, compact, and so on. Yeah. Kailangan ko palang dagdagan yung assumption ko. Dahil rewind. So, magko-consider ako ng isang monotonically Eto, nakahanap na ako ng lusot. Wag niyo nang erase yung sinabi ko kanina. Ito yung problema kapag on the spot nagpo-prove, no? So, pero anyway, at least kasama kayo sa thinking process. So, okay, ang gagawin ko, magko-consider ako ng isang monotonically increasing function, isang monotonically increasing sequence sa loob ni K. Dahil si K ay bounded, ibig sabihin yung monotonic increasing sequence na yon will converge by the monotonic convergence theorem. Yun yung hindi ko naisip kanina na nagsasalita ako ng marami. So dahil meron akong sequence na monotonic increasing, siya ay convergent. Tapos dahil si K ay closed, lahat ng sequence na nagko-converge sa loob ni K ay may limit na nasa loob ni K. So yung limit ng monotonically increasing sequence na kinonsider ko ay nasa loob ni K. Pero alam na natin sa proof ng MCT ng limit ng isang monotonically increasing sequence ay yung supremum. Alright? So using that argument or a generalization of that argument, you can show that ang supremum niya ay nandoon sa loob ni set K. Tapos ganoon din yung sa pagiging pag-exist ng infimum sa loob ni capital K. So gagamitin yung pagiging bounded at pagiging closed ng compact set plus I guess the MCT para masabi na nga yung supremum at infimum niya ay nandoon sa loob ng set K. Okay, think about that. Baka lumabas siya sa problem set. All right, so baka lang naman, ano? Now let's see the proof of not the lemma, but the proof of the extreme value theorem. And this is very important, especially for optimization and other applications. Sa machine learning, gamit na gamit din yung extreme value theorem kasi optimization based yung mga nasa loob ng machine learning tools natin. But that's too much for us. Tingnan na lang natin muna yung proof ng EVT. Okay? Okay. So ang assumption natin dito ay si F ay continuous, tapos si K ay compact. Gusto nating ipakita that F attains a maximum and minimum inside of K. All right. So let's see. K is compact. So by Theorem 3.5, the preservation theorem, yung F bracket K ay compact pa rin. Okay? Dahil si F bracket K ay compact, then by lemma 3.1, yung supremum at saka infimum ni F bracket K ay nag-exist. Alright? So tawagin natin Z sub little m, yung infimum, at yung C sub big M, siya yung supremum. And both of these guys belong to F bracket K by lemma 3.1. Yung supremum at infimum ng isang compact set ay nasa loob ng compact set na yon. Okay? Dahil si ZM, si Z sub little m at saka si Z sub big M ay na kay F bracket K, then ibig sabihin function value sila ng ilang miyembro ni capital K, right? Kasi nga naka F bracket K siya, so function value siya ng some member of capital K. So let's say x sub little m is the pre-image of z sub m, that is z sub m equals f of x sub m. Tapos si x sub capital M, siya naman yung magbibigay sa atin ng function value na c sub m. Okay? And then from there, we can just say na by definition ng infimum at supremum, yung mga f of x's, these are the members of F bracket K, ay bounded below by f of x sub m, kasi nga ito yung infimum, and then they will be bounded above by the supremum. And the nice thing about this is that this is a function value of a member of capital K, and this is a function value of a member of capital K. So, ibig sabihin, yung maximum at minimum ng isang function sa isang compact set ay nandun sa loob ng compact set na yun din. Right? And that's what the EVT tells us. Okay? Medyo madaya, no? So, kasi yung bulk ng work ay ginawa na nung lemma 3.1. That's why I want you guys to take a look at the proof of lemma 3.1. Okay? And I think that's all that I want to say about compact sets or continuity over a compact set. All right. So kung hindi man na-preserve ng continuous function, ang pagiging open or pagiging closed ng isang set, na-preserve naman niya yung compactness. And the preservation theorem for compactness gives us a nice significant result, namely the extreme value theorem. Okay. Any questions before we leave the section? Okay, so kung walang tanong, proceed tayo sa section 3.5. Ayan, patapos na yung unit 3, so talagang papunta na tayo sa exciting part. And that is the problem set, which we can talk about later. Okay, so tingnan natin. Uniform continuity. So, ang nangyayari, ang tema kasi ng Unit 3 ay pagtatahi ng konsepto ng limits, continuity na natutunan natin sa Math 36 papunta sa counterpart nila sa limits of sequences, which we tackled briefly in Math 38, but we talk about in details in the previous unit, right? Now, merong isang klase ng continuity that mimics what happens for Cauchy sequences. At yun yung konsepto ng uniform continuity. So, remember yung pagiging Cauchy. So, sabi natin, ang isang sequence ay Cauchy if and only if in the long run, yung mga function values nila ay dikit-dikit na. So, as you go further away in the list, the terms in the list becomes closer and closer to each other. Yun yung pagiging Cauchy. Alright? So, at alam natin lahat ng Cauchy sequences ay continuous and vice versa. Lahat ng continuous functions ay Cauchy. All right? At least on the realm of real numbers. And that's the Cauchy convergence criterion way back in Unit 2. Okay? Now, paano natin may extend yung konsepto ng pagiging Cauchy sa real valued functions? And I guess the closest analog that we will get would be uniformly continuous functions. Okay? Now, the idea about uniform continuity is kapag magkakalapit na yung mga x values, all right? So kung super lapit na ng mga x values sa isa't isa, yung mga y values din nila ay magiging malapit na rin sa isa't isa. Okay? And basically, that's what pagiging cushy is, right? Pagpalayo ka na ng palayo sa listahan, ibig sabihin, palapit na ng palapit yung mga terms ng sequence sa isa't isa. So, ganun din sa functions na ang domain ay subset ni R. Kapag palapit na ng palapit yung mga x's, there's something special if the function values of those x's become very, very close to each other also. Okay? At yun nga yung uniform continuity. And one way to characterize uniform continuity is to revisit our definition of continuity. And then ang mangyayari ron ay dapat yung choice natin ng delta ay hindi nakadepende dun sa x value. Alright? Kasi kung hindi siya nakadepende sa x value, then dun sa epsilon delta definition, kung si delta ay hindi dependent sa x value, ibig sabihin we can make delta arbitrarily small regardless of how x sub 0 is compared to x or gaano kalayo si x sub 0 mula kay x. So ang idea, para ma-quantify yung gusto kong mangyari na kapag magkalapit na yung mga x's, dapat magkalapit na yung function values nila. That is the choice for delta insofar as the epsilon delta definition of continuity or limits is concerned ay dapat independent sa x sub 0. Okay? So dapat meron kang isang delta na mag-work sa kahit na anong x. Hindi siya dapat nakadepende kay x sub 0. Okay? Tingnan natin yung mga examples na nakita natin before. Look at the linear function f of x equals x. If you do the preliminary analysis, you will see that if you're given an epsilon greater than 0, you can choose delta to be equal to epsilon. And note here that our choice for delta depended only on epsilon, regardless of what x sub 0 is. So kahit pa saan mukunan ng limit si f of x, as x approaches any number of your choosing, lagi mong pipiliin na delta ay si epsilon. So hindi nagmamatter kung anong number yung ino-observe mo. Kasi kahit na ano pang number yung kung saan kinukunan mo ng limit yung function na f, hindi nakadepende ron yung choice mo ng delta. Pag binigyan ka ng epsilon, ang delta mo automatic ay equal kay epsilon. And that will imply, or that will give us the delta inequality implying the epsilon inequality no matter what x sub 0 is or how far away it is from x. So ito yung sinasabi natin that the choice of delta is independent of the choice of x sub 0. Okay? And actually for any linear function that is true, because if you have a linear function f of x equals ax plus b, where a is not equal to 0 para maging linear function siya, remember that our choice of delta is epsilon over absolute value of a. And you see that this formula for delta doesn't involve x sub 0. This will work for any x sub 0 that you choose. Okay? So in a sense, we can say na, okay, mukhang may chance na maging continuous function, na maging uniformly continuous yung function f. Kasi nga, ang notion ko ng uniform continuity, gusto ko kapag magkakalapit na yung mga x's, magkakalapit na rin yung mga y's nila. Okay? And this will happen for any element of the domain. Kaya ang tawag ko sa kanya uniform continuity. Kasi kahit ano pa si x sub 0, kung saan ino-observe mo yung continuity, dapat uniform yung choice natin of delta. Okay? And this is not always the case. For instance, you consider the quadratic function x squared. Now, we know that g is continuous because it's a polynomial, all right? So dahil siya ay polynomial, continuous na siya, pero para ma-prove yung continuity, right, sa kanyang domain, kapag binigyan tayo ng x sub 0, kung saan gusto natin na element ni domain, yung choice natin for delta, for some real number epsilon, or for some positive real number epsilon, ay equal dito. Minimum ni 1 over epsilon over 2 times x sub 0 plus 1. Okay? And you see that obviously the choice for delta will now depend on x sub 0. And no matter how you do the preliminary analysis, your choice of delta will still depend on the choice of x sub 0. All right? So kahit sa sabihin mo, okay, sir, paano pagka ginawa ko, inassume ko na yung x minus x sub 0 ay less than 100. So magiging minimum to ng 100, some expression. But I guarantee you that yung expression na yon, napapalit dito, ay nakadepende pa rin kay x sub 0. So that means, pag nagpo-prove tayo ng continuity of the quadratic function x squared at a number, nakadepende yung choice natin for delta to that number. Halimbawa, you're proving that x squared is continuous at 4. So kung gusto mo ipakita na si x ay continuous kay 4, one way to do that is to choose your delta to be the minimum between 1 and epsilon over 9. Okay? Kapag ka naman pagka ang chine-check mong continuity ay kay -1, alright? Ang delta mo naman ay yung mas maliit kay 1 at saka kay epsilon over 3. Alright? So this means that the choice of delta vary from x sub 0 to x sub 0. And in that notion, nakadepende pala kay x sub 0, okay, kung ano yung delta. So kung gaano dapat kalapit yung mga x's kay x sub 0 para yung mga function values nila ay maging mas malapit na rin sa isa't isa. Alright? So nakadepende. Meron siyang local behavior. Nakadepende kung nasa ang portion ka ng graph o nasa portion ng domain ang kinoconsider mo para masabi na siya ay continuous. Yung delta na kailangan mo sa x-axis ay nakadepende kay x sub 0. So in that sense, since the choice of delta is not uniform or is not common to all x sub 0s, then we say that g of x equals x squared is not uniformly continuous. Okay? So ito yung una nating natutunan dito, ng isang function ay pwedeng maging continuous pero hindi uniformly continuous. But we will see later that the converse is true. Na kapag ka ikaw ay uniformly continuous, automatic ikaw ay continuous. And that is easy to see. Actually, it's not worth even writing as a theorem. Kasi nga sabi natin, kapag uniformly continuous ka, kapag ka yung choice of delta mo ay independent kay x sub 0, so in the first place, there's a way to choose delta. And it can be chosen in a much rigorous way. We choose delta to be independent of x sub 0. So kapag ka ikaw ay uniformly continuous, automatic ikaw ay continuous. Pero kapag ka ikaw ay continuous, hindi ibig sabihin na ikaw ay uniformly continuous. Okay? So I think there's another example that we have met before that is continuous but not uniformly continuous. And that is the square root function. We said this is continuous on the closed interval 0 to positive infinity. All right? Pero nung nag-preliminary analysis tayo, ano yung ginamit natin? Kapag kasi x sub 0 ay hindi 0, ang choice natin ng delta ay square root of x sub 0 times epsilon. Alright? So, nakalimutan ko kung ano yung choice natin kapag kasi x sub 0 ay 0. Ano yung delta na ginagamit natin. Pero anyway, for numbers aside 0, ang choice natin for delta ay square root nung number na yon times epsilon. And actually, I can guarantee you as well na kahit na ano pang choice ng, kahit ano pang preliminary analysis yung gawin nyo, yung choice of delta nyo nakadepende pa rin kay x sub 0. So the square root function is not uniformly continuous. Kasi nga yung choice of delta ay nakadepende kay x sub 0. All right? Now, with that in mind, we can formally state the definition of uniform continuity. Okay? So function f is said to be uniformly continuous on the set E, or on its domain E, if and only if for all epsilon greater than 0, there exists a delta greater than 0. So tipong ano pa rin siya, definition of continuity. But here we note that delta depends only possibly in epsilon, not on x sub 0. Okay? Kasi makikita nyo dito, wala nang mention of x sub 0. So it is continuous, it is uniformly continuous on the set E if and only if we are given an epsilon greater than 0, we get a delta that is independent of epsilon, such that for all elements x and y of the domain E, whenever the difference between x minus y or between x and y has absolute value less than delta, then f of x and f of y will be arbitrarily close to each other. Okay? One thing to note here is the notion of uniform continuity is only defined on sets. Yung continuity natin, meron tayong continuity at a number at meron tayong continuity at a set. All right. Pero when you're talking about uniform continuity, it's always about uniform continuity on a set. Okay? So ibig sabihin, uniformly continuous ang isang function sa isang set E kapag ka yung dalawang members kapag ka yung dalawang members ni E ay arbitrarily close to each other, then their function values will be arbitrarily close to each other as well. Which reminds me of the Cauchy sequences na nagiging magkakalapit na sila na magkakalapit sa dulo. Right? So, yun pala yung sinasabi ng uniform continuity. Kung gusto mo na yung mga function values ay magiging magkalapit na magkalapit, alright? Kaya mong i-require yon by saying na yung mga x's dapat ay magkakalapit din sa isa't isa. Okay? Does that make sense, guys? Medyo bugbog na kayo sa dami nating dinidiscuss today. Okay pa ba? Or kaya nyo pa ba, guys? Tingnan ko kung ano pa yung natitira. Habang inabsorb nyo yung definition. Konti na lang. Alright. So, kung wala kayong objections, sige, tuloy na lang natin dito sa Theorem 3.8. Then let's call it a day. Alright? Kasi baka masyado na tayong maraming napag-usapan right now. So, yun yung definition ng uniform continuity. Pero again, itatali ko na naman to sa konsepto ng sequences. Okay? And that's what Theorem 3.8 is for. So, Theorem 3.8 tells us that a function f will be uniformly continuous on a set E if and only if for any two sequences in the domain, all right, the convergence of the sequence xn minus yn to 0 implies the convergence of the sequence of the differences of function values to 0. So kahit anong dalawang sequence na kunin ko, na yung sequence na mabubuo by subtracting their members ay nagko-converge kay 0, then automatic daw na magko-converge yung sequence ng mga function values, yung sequence ng difference ng mga function values ay magko-converge din kay 0 if and only if f is uniformly continuous. Okay? So, pero actually mahirap gamitin tong 3.8 in practice. Yung corollary niya yung gagamitin natin, yung criterion para masabi ng isang function ay hindi uniform continuous. Kasi hindi uniformly continuous. Kasi yung Theorem 3.8 sinasabi niya na kapag siya uniformly continuous if and only if this is true for any two sequences. So para ma-conclude yung uniform continuity, kailangan i-check mo lahat ng sequences na nasa loob ni E na totoo tong implication na to. Pero that's hard to do. We cannot enumerate all pairs of sequences inside of the set E. So, pero it's a nice theoretical result because this gives us a more operational way of dealing with uniformly continuous functions. Hindi nga lang siya practical to conclude uniform continuity. Pero kung sure na ka na siya uniformly continuous, then we can use this statement for proving succeeding theorems. Okay? So let's try to read the proof, all right? Ng Theorem 3.8. It's an if and only if statement, so it needs two parts. So dalawang parts yung kailangan natin sa proof, yung forward at saka yung converse, okay? Tingnan natin yung forward. Paano pinrove yung forward? Yung sa forward proof, i-assume natin na si f ay uniformly continuous. Okay? Tapos gusto nating ipakita na pag nag-consider ako ng kahit na anong dalawang sequence such that the limit of the difference of the members of those sequences ay nagko-converge kay 0, then automatic dapat magpa-follow na yung sequence ng difference ng mga function values ay magko-converge din kay 0. Okay? So, the proof was done this way. Ginamit yung definition ng pagiging uniformly continuous. So uniformly continuous siya if for all epsilon greater than 0, there exists a delta greater than 0 such that this inequality is true, coming from the definition. Okay? Then we will assume, kasi conditional proof yung gagamitin natin, i-assume ko itong part na to. So I will assume that the limit of some sequence x sub n minus y sub n is equal to 0. Okay? So in-assume ko yan, then gagamitin ko yung definition ng limit ng isang sequence. Alright? Since xn minus yn converges to 0, then there exists a delta greater than 0. Such that for any epsilon kasi nasa definition ng convergence ng sequences, that will be true for any epsilon greater than 0. But I have a delta here that is greater than 0. So for that specific delta, okay, which is greater than 0, we can find a starting index such that after that index, yung x sub n minus y sub n minus 0, remember, ito yung sequence, ito yung limit, all right? So kapag ka malaki na yung subscript, yung x sub n minus y sub n minus 0 will be less than delta. Alright? Kasi 0 yung limit ng xn minus yn, so nawala lang siya doon. Pero yun yung kung bakit nakuha natin ito. Then, nakita ko ngayon, ang absolute value ng xn minus yn ay mas maliit kay delta. Pero sabi nung nakuha natin sa definition, kapag ka may dalawa kang numbers ng absolute value ay mas maliit kay delta, magpa-follow yung epsilon inequality. So from here, I know that f of xn minus f of yn will be less than epsilon. All right? And this essentially is the definition of the convergence of xn minus yn to 0, because for any epsilon greater than 0, we had found a starting index capital N such that for all little n greater than or equal to capital N, etong inequality na to ay totoo. That means yung fn minus, yung fxn minus fyn ay nagko-converge kay 0. Which is what we wanted to show in the forward implication. All right? So, kalahati na lang yung kulang. Kailangan nating i-prove yung kabila. Na kapag totoo ito sa kahit na anong dalawang sequence xn and yn in the domain, dapat magpa-follow na si f ay uniformly continuous. And we will prove the converse by contradiction. So, i-assume natin na totoo ito. All right? Totoo itong implication na to sa lahat ng pair ng sequences dun sa domain. Tapos, I will suppose for the sake of contradiction that f is not uniformly continuous. And I will show that something will be wrong if I will accept that to be true. All right? So kung i-assume natin na si f ay hindi uniformly continuous, then may makikita tayong epsilon greater than 0 na sa lahat na lang ng delta, specifically sa mga delta ng itsura ay 1 over n. Okay? Yung delta inequality ay mag-hold, pero yung epsilon inequality ay baliktad. Negation lamang nung definition ng uniform continuity. Alright? So we have this delta inequality implying the negative o yung negation nung epsilon inequality. Okay? So, but this guy can be translated to the limit of x sub n minus y sub n being equal to 0. Okay? Kasi nga, ang xn minus yn ay laging mas maliit sa 1 over n. So, sure tayo na yung xn minus yn ay papalapit ng papalapit kay 0. Kasi nga, mas maliit siya sa lahat ng 1 over n. So, definition ng limit ng isang sequence. So, we now know that the limit of xn minus yn is equal to 0. Oh, but that is part of our assumptions. Remember that the assumption in the converse case is kapag ka nakakita ka ng sequence na ganito yung limit property, then magpa-follow na ito. Yung limit ng function values nila ay equal kay 0. Okay? So, pero, ano yung meron dito? Meron dito sinasabi niya hindi totoo yung epsilon inequality for some epsilon, specifically epsilon sub 0. So we cannot reconcile the fact that this being true implies yung limit ng f of xn minus y sub n ay equal kay 0 vis-a-vis the assumption that the limit is not equal to 0. All right. So that means, yeah, yun yung hinahanap natin na contradiction. Because f of xn minus f of yn cannot be convergent to 0 and not convergent to 0 at the same time. All right? And so we must reject the supposition. So ibig sabihin si f ay automatically uniformly continuous. All right? So does that make sense? Any questions? Or dina-digest pa? Na-absorb nyo pa? Or andyan pa ba kayo? Okay, yeah, that's fine, Michael. Yeah, kailangan talaga it takes some time, right? So what I suggest kung basahin niyo uli yung proof later, or you can rewrite the proof. I guess the best way to understand proofs is to rewrite them. Kahit may proof yan na nasa lecture notes, pwede mo yan tingnan, tapos i-convert mo siya into your own words kahit kaharap mo siya, nababasa mo siya, tapos sulat mo siya in your own words. Insert some details kasi usually sa books, may kulang dun sa mga proofs. Hindi nila sinusulat lahat ng mga kailangan dun sa proof. So it would be a nice exercise to write it on your own words and insert as much details as you can. Yun yung ginagawa ko, and siguro yun na rin yung sakit ko. Pag nagpo-prove ako, laging nandun lahat ng detalye. Alright? Unless tinamad akong isulat kasi sobrang haba. Pero yeah, kung ano yung script ko, pagka dinidiscuss ko siya, ganun ko siya gustong isulat yung proof. Pero not all books will do that. Alright? Medyo siguro intentional na rin para yung readers kasi makuha yung practice na nag-i-insert ng details doon sa proof. Okay? But let's stop here. We'll just continue on Monday. On Tuesday. Konti na lang yung results. 2 more results in 3.5. And we can go to the intermediate value theorem. And that will conclude Unit 3. Okay, and that means we'll have the problem set. So I'll give you the problem set probably when? I'll give it to you towards the end of next week. And then I'll give you 5 working days to finish it. Is that okay, guys? Siguro ibigay ko siya by... Kailan ko siya... Bibigay ko siguro siya ng Thursday. Gusto niyo ba Thursday? So bibigay ko siya ng Thursday, late Thursday. Okay, para sure na kung ano matatapos natin by Thursday. Pero I expect to finish it by Tuesday. Bibigay ko siya ng Thursday night. So, ibig sabihin, meron kayong Friday, tas Monday, Tuesday, Wednesday, Thursday. So, Thursday after next, yung magiging pasahan ng ating problem set. Right? So, I'll probably give you 3 questions or 4 questions para doon. O sige, 3 questions na lang yung ibibigay ko. Hindi 3 questions lang. 3 numbered items, alright? So tapos may maliliit na sub-questions o mga mini tasks sa loob ng mga questions na 'yon. Para 3 'yon, tapos 5 araw kayo mag-work. So that's fine. You just need to do around 3/5 ng isang problem a day, then you'll be on a good pace, okay? Plus the weekends kung nag-work kayo pag weekends. So yeah, let's plan on that. Pero meron pa tayong isang homework. Bibigyan ko kayo ng homework for tomorrow. Okay? Bibigyan ko kayo ng homework tomorrow which will be due on Tuesday next week kasi ang usapan nga pala natin homeworks tayo. Right? So, maiksi lang naman and I'll design it so that it would be a nice exercise or a nice prelude to the coming problem set. Okay? All right. I think that's it. Questions, guys? Concerns? Okay, so kung wala na, I hope you guys have a nice day and enjoy the weekend. And let's see each other again on Tuesday. Watch out for the homework tomorrow. Deadline will be on Tuesday as well. Bye, guys.